So hello everybody. First of all, I would like to thank the organizers for inviting me. It's a great honor to be here with so famous researchers. And since I'm head of Bayesian methods research group, it's not surprising that I will talk mostly about Bayesian methods and about how they can be combined with deep learning. So first, we'll briefly describe Bayesian framework and its scalable modification known as stochastic variation inference. Then we'll review what is dropout and how it's related to Bayesian regularization. And finally, we'll end up with a sparse variational dropout, which is an example of quite successful combination of Bayesian methods and deep neural networks. And probably the idea of my talk can be summarized by the following picture, which I do like a lot. So here I say that we are the Bayesians, and we will simulate all your weapons, and we'll use it as a particular case of our own, so the further resistance is useful. So during the rest of my talk, I will try to convince you that this picture at least partly true. So of course everybody knows what is Bayesian inference. So we were given data from some distribution known up to parameters, and we are lucky enough to encode our ignorance about these unknown parameters in terms of distribution. Then the best way we can do is to perform Bayesian inference and to end up with a posterior distribution which contains all available information we could extract from data. So this is the most optimal way of how to proceed. So any kinds of simplifications, such as using point estimates or interval estimates, inevitably lead to some loss of information. So, and posterior distribution contains the whole information we could extract from our data. So how it can be applied to machine learning? So consider the standard formulation. We're given training set xt, where x are features, t are hidden labels, and we are given probabilistic classifier, which returns us the probability of hidden variable given the observed variable and given some weights to be adjusted. So if we define a reasonable prior p of w, then we may construct Bayesian procedure. And training and test stages differ a bit from how we solve machine learning in classical way. So during training stage, instead of searching for the single classifier, we are searching for the ensemble of classifiers, and the ensemble is given by posterior distribution p of w given xt. So this is simply the application of Bayes theorem. And at the test stage, again, instead of applying just single classifier, we perform weighted voting. So we apply the whole ensemble, and the weights of the elements of this ensemble are equal to the value of posterior distribution p of w given xt. So this is how it should work in theory. And the Bayesian framework provides us the way of how to train the ensembles. But almost nobody uses it in practice. Why? Because of these two parts. So these are integrals. The integrals are intractable, and the dimensionality, if we are talking about deep neural networks, so the dimension of W is of orders of millions. So that's completely impossible even to very roughly estimate these integrals. And this was the reason why Bayesian methods were not so popular for large-scale machine learning problems until very recently. And probably it was about 6 years ago when David Bly has published a paper on stochastic variational inference, where a very nice idea was suggested. Instead of solving inference problem, let us solve optimization problem, because we know how to solve large-scale optimization problems in a quite efficient manner. So instead of trying to compute the posterior distribution, let us try to approximate it by some distribution from parametric family, which we call variational distribution, Q of W, from parametric family, which is parameterized by phi. And we will try to find this distribution by minimizing some distance measure. You can take various distance measures, but probably the most popular one is KL divergence between variational approximation and the two posterior distribution. So it can be easily shown that minimization of this KL divergence, so the KL divergence itself is still intractable, but it can be shown that its minimization is equivalent to optimizing of ELBO, evidence or bound. And although this ELBO is still intractable, we may optimize it using stochastic optimization framework. So because it has several very nice properties. One of them is that we can easily compute stochastic gradient. Why? Because here the log likelihood of training sample, the likelihood of training sample is under logarithm, so we may represent it as a sum over the objects from the training set, and we may compute stochastic gradient using many batches of data. And this is an expectation, and an expectation can be, again, easily approximated with a Monte Carlo estimate. So the computation of stochastic gradient is quite easily, and although we cannot compute the function itself, we may more or less efficiently optimize it using stochastic gradient descent or any kinds of its modifications. Another good thing is that we can't overfit. So the richer is our variational approximation family. The richer is Q of W family of distributions. The closer we are to the true posterior, to the P of W given xt. And finally, we may rewrite ELBO as follows. So we may split it into two terms. And we may interpret the first term as a data term, while under the second term as a regularizer. So if we forget about the second term, and if we try to solve to find the optimal Q by optimizing just the first term, we may easily see that the optimal Q is just a delta function at maximum likelihood point WML. So this is why the first term can be called data term. While the second term prevents us from collapsing to delta function. So it penalizes if we deviate too much from the prior distribution. And due to the second term, we end up with some non-degenerate variational approximation, Q of W. So this is really ensemble rather than a single classifier. And looking at this ELBO, we may think about a new understanding of what regularization really is. So classical understanding of regularization is simply adding some additional term to our criterion and optimizing this regularized criterion with respect to W. But when we tell about variational Bayesian inference, instead of optimizing with respect to W, instead of optimizing some regularized criteria, we optimize with respect to phi. So we actually train the ensemble, not single classifier. And if we train it in a stochastic manner, so if we use stochastic optimization, and this is the only way we can use, we may easily see that actually this procedure is very similar to noise injection, to the injection of noise during training. And this looks pretty much the same like non-dropout procedure. So now we switch to dropout. So this is known as pure heuristic procedure, which is somehow works. So there are several variants of dropout. One is binary dropout, which corresponds to injecting of Bernoulli noise to the weights or to the outputs of neurons. Or another variant is Gaussian dropout, when we inject Gaussian noise with a mean of 1 and the variance of alpha. So the performance of dropout is highly dependent on how we choose dropout rate P or how we choose the magnitude of Gaussian noise alpha. And it is assumed that those hyperparameters should be set up manually. So about a year and a half ago, Kingmas, Elements, and Welling decided to understand whether this dropout, whether this noise injection procedure correspond to some variational Bayesian inference. So they decided to understand whether we may write down the Gaussian dropout procedure as optimization of some ELBO. So we may easily see that in this case, the variational approximation looks like this. So this is a factorized normal distribution with respect to all the weights with a mean of theta and a variance of alpha theta squared. Why so? Because this is exactly the result of what will happen if we take the weights theta and we'll multiply it by the Gaussian noise with a mean of 1 and a variance of alpha. So we'll end up with such distribution. So, and then the corresponding ELBO looks like this. And the first term is actually exactly the thing we optimize during Gaussian dropout procedure. Because this is our training log likelihood. And what we do on each iteration of Gaussian dropout training, we noisify the weights. So we sample from this distribution. We sample from this distribution, and we compute stochastic gradient with respect to the true weights, which are theta. So we optimize the first term with respect to theta. But in ELBO, we have two terms, the first term and the KL term. In Gaussian dropout training, there's no KL term. And the brilliant idea was maybe we could find such prior distribution, POW, that this KL term will not depend on theta. And if so, then these two procedures become completely equivalent. So this will mean that Gaussian dropout training really corresponds to some variational Bayesian inference with some specific choice of prior distribution POW. And well, these three guys managed to find such prior distribution POW, and surprisingly, it appeared that it is very interpretable. So it corresponds to improper log uniform prior distribution. So distribution which is improper, but up to normalizing constant looks like this, so 1 over absolute value of W, and it's factorized with respect to all the weights W's. So it looks approximately like this, and it is interpretable because it's roughly speaking, it penalizes the precision with which we find the weights of our neural network. So the more significant digits we find, the more penalty we have to pay. So this is some nice interpretation. And using this prior distribution, we immediately show that our KL term between our variational approximation and this log uniform prior doesn't depend on theta. Of course, it should depend on alpha, because it has to depend on some variational parameters. So it doesn't depend on theta, but it depends on alpha. But still alpha is fixed in our Gaussian dropout procedure. These two algorithms are equivalent. But now, we know that actually during Gaussian dropout, we perform variational inference and we optimize the sum of two terms, data term and KL term. Then the question arises, why not to optimize this ELBO with respect not to just theta, but with respect to theta and alpha? Is it possible? And the answer is yes. In order to do this, we first need to understand how to compute this KL divergence and how it depends on alpha. But fortunately, this KL divergence can be split into sum of one-dimensional KLs. And each one-dimensional KL can be approximated using analytic functions. So this is the illustration. So the black dots are the real values of KL divergence with different alphas. And the three lines are three different approximations. The first two are from the paper from Variational Dropout by Kingmas, Elements, and Welling. The red one is our approximation, which allows us to approximate KL divergences even with for the large values of alpha. So using this analytic approximation, we may more or less efficiently optimize ELBO with respect to thetas and with respect to alpha. So we may find hyperparameter alpha, the magnitude of our Gaussian noise we inject during training, in a Bayesian manner automatically. But we can do even further. If we can optimize with respect to alpha, then why not to assign individual alpha for each individual weight? So we take weight Wij and we assign it individual noise magnitude alpha ij. So this is much richer family variational approximation, but as I stated before, the richer approximation family we have, the closer we are to the true posterior distribution. So we are not overfitting. And another nice thing is that it can be shown that if alpha ij goes to infinity, then we may show that theta ij, the mean of this variational approximation, should go to 0 in such a way that alpha ij times theta ij squared goes to 0 as well. So this means that if alpha goes to infinity, then this term boils down to delta function at 0. And delta function at 0 simply means that we may remove the corresponding weight, we may remove the corresponding connection. And here, again, we may make some analogies with one of the previous talks, where the speaker talked about sparse deep neural networks and about the quantity of relevant connections we really need in DNNs. So this appears to be a surprisingly efficient way of removing redundancy from DNNs. So It's not a secret that current DNNs are highly redundant, but the problem is that nobody knows how to remove this redundancy. Because if we try to use okay, there are some research, but in practice it appears that if we try to train simple neural networks, we end up with a worse quality. So one possible way is to perform this distillation and to use dark knowledge. Another way is to take very large DNN and then to train it and then try to remove the unnecessary connections. So far so good? Not yet. There is one serious problem with the stochastic gradients. So in order to be able to differentiate our ELBO with respect to variational parameters that are theta ij's and alpha ij's, we need to use this chain rule. So we differentiate ELBO with respect to W and then W with respect to theta. And under this parameterization, so when our variational approximation is approximated as false, as normal distribution with a mean theta and the variance alpha theta squared, of course we use reparameterization trick, so we express W as follows. But then when we differentiate it with respect to theta, we end up with this quite unpleasant expression. Why it's unpleasant? The reason is that, so this is stochastic gradient. Epsilon is just a random variable, normally distributed with a 0 mean and a variance of 1. And the problem is that the variance of this stochastic gradient becomes huge when alpha is big. So this is one of the reasons why in this parameterization it's not possible to optimize alphas in the whole range from 0 to infinity. But well, quite obvious trick is applicable here. So we establish new variable, which is actually quite old variable. This is classical parameterization for normal distribution. So this is sigma ij squared, which is equals to alpha times theta squared. And under this parameterization, we may easily reparameterize W, and the corresponding stochastic gradient, its variance is limited by the variance caused by mini-batching. Of course, in this parameterization, KL term now becomes dependent on theta. So in parameterization theta alpha, KL term didn't depend on alpha. In parameterization theta sigma, KL term depends on theta, but quite straightforwardly. So we may easily differentiate it by differentiating first KL with respect to alpha and then alpha with respect to theta. So this is how it can be done, and this is the comparison of two different parameterizations. So we may see that theta sigma parameterization converges much faster in terms of ELBO. So this is blue line in comparison with the theta alpha parameterization, which is shown in green. And what is interesting is the 1 minus sparsity, so the number of non-zero weights. So we see that the sparsity is really quite impressive, and again, the convergence is much faster than in the old parameterization theta alpha. And here's one more illustration of how it works. So this is a simple experiment on LeNet 5 convolutional neural network, and the similar results were obtained with a VGG16. So to the left are examples of some convolutional kernels, while to the right is a fragment of weight matrix from one of fully connected layers. And so we may see that the sparsity is really quite impressive, so more than 99%, while the compression is about 215, and pay attention that the accuracy does not degrade. So we really end up with an extremely sparse DNN. Another interesting thing is this famous experiment by Sami and his colleagues about randomly permuted labels. We show that modern DNNs can catastrophically overfit. So if we apply this sparse variational dropout to the problem where the labels are randomly permuted, surprisingly, well, maybe not surprisingly, we end up with a neural network where all weights have been removed from the neural network. So neural network just refuses to solve the problem where the labels were randomly permuted. And again, this is quite nice, and this corresponds well with non-Bayesian interpretation that Bayesian framework is just mathematical formulation of Occam's razor. So the simplest possible explanation, and in the case when all labels are randomly permuted, probably the simplest possible explanation is to say that you should label data only with a random guess. So no algorithmic mean exists that is available that is able to classify data given random labels. So probably this is all I wanted to say, and this is where I will conclude. To conclude, Bayesian framework is a quite powerful tool, and now we have we know how to scale it up, how to apply it to large-scale machine learning problems, and even the first attempts of marrying Bayesian framework with DNNs already lead to quite surprising and quite interesting results, and probably many more to come in next years. Thank you.
Plenty of time for questions. David?
So it was very interesting to hear that the network apparently couldn't learn anything if all the labels were wrong. Did I understand that right? That all the weights were removed?
Yes.
Yeah. Yes. So could you actually condition the term on each individual sample and thereby get an estimate for the probability of the label being wrong in a real data set?
Well, that DNN already returns the distribution over the labels. So you may see just, you may look at the distribution and and estimate, say, its entropy for the particular sample, and using this to understand whether the network is pretty sure or not in its labeling. So here the task was a bit different. So we wanted to say what will happen with the weights, with the network, if we fed it completely wrong data. Not just a single object which is wrong, but the whole data is wrong. So probably it's interesting to see how robust is the procedure if we start increasing the number of wrongly labeled objects. So probably up to some extent neural network will be still able to learn, and at some point it will just collapse to zero network.
Thank you. Just adding to this, I think since we have kind of similar experiments in this setting, I think what happens for an increasing number of random labels is that if the network was perfectly efficient, then it wouldn't really matter for the network whether it would fit the label or not. Since networks are not perfectly efficient, they don't quite manage to fit random labels for the critical value of variational inference. So I would say that if you run your experiment with like alpha of the labels random, you will only fit the alpha of the labels that are not random. I think at least in our experiments, something like this happens. So I would say in your framework, it should work pretty similarly.
Probably.
Rich?
So a question, you used the word ensemble a number of times, and you said that the Bayesian model is optimizing for the ensemble.
Right.
Now, when I think about ensemble in classical machine learning, you know, I expect the ensemble to be more accurate than any of the individual models that are in the ensemble. Does this match what you're...
Yes.
So I guess I thought of Bayesian ensembles as being more of like hedging their bet. You know, they think the model is one of the models in the ensemble, and then they don't have enough evidence to do model selection, so they're hedging their bets. But you're actually talking about ensembles that you expect to be more accurate than any of the individual models in the ensemble.
Okay, so first of all, here we use just a single neural network. So we're training the ensemble, but we're using just MAP neural network. But we also experimented with what happens if we generate several neural networks from our posterior distribution, then average up the results. The results are really better. So averaging really helps. The problem is that in practice, it's it's quite inefficient to perform this averaging because you need to average not with respect to, say, 10 neural networks, but with respect to, say, 100 or 500 neural networks. So the testing time greatly increases. And this is bad for the industry, for the production. So this is why I think that quite promising ways to perform this distillation, either Bayesian distillation or non-Bayesian distillation, and to train a student neural network that is able to simulate the whole ensemble. What is good here is that we do not need to keep the whole ensemble in memory. All we need to keep is to keep a variational distribution, which is quite simple, or at least for this kind of model. And then you simply need to generate samples from this posterior distribution, substitute it to the neural network, and get the result, and then average the results. So this is quite a compact way for keeping the whole ensemble in memory.
Is the method trying to simultaneously optimize the diversity of the models in the ensemble as well as their accuracy, so that the ensemble has, you know, good final variance reduction, or?
Yes.
Cool.
Due to this term here. So this term is actually responsible for the diversity. Because if we remove this term, then we will end up with the best DNN we can find, well, at least in theory. This is WML, maximum likelihood point. But it will not be diverse. So the second term is responsible for the diversity.
So in your method, you can find sparse W, but I wonder if choosing the good structure of the deep neural networks is still important, or you can just use some large enough model and do for any data?
Well, I would say that it is still important because, well, it's. I would like to say that the simple solution, just take very big DNN and then simply sparsify it. But the problem is that the greater DNN we have, the larger computational difficulties with its training. So it's not so easy to train it perfectly. So this is why I think the initial choice of a structure of DNN is still important.
Okay, let's thank all the speakers.